So in this video, we're going to talk about some introductory concepts and vocabulary related to acids and bases. And then in the next video, we'll talk about how we measure the concentration of acids and bases using either the ion concentration or the pH scale or the pOH scale, and how we can do that. So first, some properties of acids and bases. Okay, physical properties, things like acid tastes sour, and if you think about lemon juice, citric acid, that's what gives it that sour taste. Lots of sodas have different types of acids in them to give them some of that bite flavor that they have. And bases tend to taste bitter. Things like dark green leafy vegetables have this in them. And bases tend to feel slippery. Things like bleach. If you get bleach on your hands, it feels very, very slippery. Soap, it tends to be a basic compound, so that will also feel slippery. Something that they have in common is that both acid and base solutions will conduct electricity, and the stronger the concentration, the more conductive they become. When you use litmus paper, which you may have done in the past, blue litmus in the presence of an acid will turn red, and red litmus in the presence of a base will turn blue. And of course, if you put red litmus in an acid, it doesn't do anything, and vice versa, blue in base won't change color. So what really makes something an acid or a base? Well, the main idea here is that acid and base is dependent on the balance between hydrogen ions and hydroxide ions. Now, the hydrogen ion you'll often see also represented as H3O or hydronium. Okay, either of these would indicate that you have an acid. And then hydroxide is the OH, polyatomic ion. So any solution that contains a higher concentration of hydrogen or hydronium is considered an acid. And if the solution has excess hydroxide, it is a base. And then the concentration of those ions makes something more acidic or more basic. And it's also important to point out here that saying that something is acidic doesn't mean that there aren't any hydroxide ions. This is an important concept. Right? There could be plenty of hydroxide ions, and there often are. It's just that there are more hydrogen than hydroxide in an acid, and there are more hydroxide than hydrogen in a base. So it's not the presence or absence of one of these ions, it's just what is the balance. Now in water, what we don't often talk about is that water will actually ionize all by itself. So water molecules will dissociate to produce hydrogen ions and hydroxide ions in solution. So in every glass of water, pure water, there are hydrogen ions and hydroxide ions. But since every hydrogen ion came from a water molecule that also produced a hydroxide, the number of ions is exactly the same in pure water. Therefore, there is no balance one way or the other, and so that's what makes water neutral, because it has the same number of hydrogen and hydroxide ions. Anything that upsets that balance will cause it to become acidic or basic. There are a couple of different definitions of what an acid or base is. The sort of most straightforward definition is what's called the Arrhenius model. And according to the Arrhenius model, an acid is a substance containing hydrogen, and when you put it in water, it dissociates to produce hydrogen ions. So because it's producing hydrogen ions in water that presumably started out with an even number, you're adding hydrogen, therefore the balance tips toward the hydrogen, and it becomes acidic. These are relatively easy to spot because generally when we write the formula of an acid, we put the hydrogen first, like HCl for hydrochloric acid, or H2SO4 for sulfuric acid. So they're pretty easy to identify. And then a base in this Arrhenius model is something that has hydroxide. The hydroxide ions are typically written at the end of the formula, so they're easy to spot there as well. And when you put it in water, it dissociates to produce hydroxide ions. So again, by adding hydroxide into the mix, we are creating a basic solution by tipping the balance to have more hydroxide than hydrogens. So again, this is a really easy model to follow because the acids are generally easy to identify because they start with an H. The bases are easy to identify because they end in OH. And that's all you need to know to tell whether something's going to be an acid or a base. And again, it's pretty easy to follow that if you put something in the water that generates hydrogen ions, it makes it an acid because now you have more hydrogen ions, and vice versa for the base. So here's examples like the one I just gave you. So hydrochloric acid, hydrogen chloride, when you put it in water, produces hydrogen ions, and chloride ions. The chloride ions have no effect on the acidity or basicity of the solution. The problem with this model, as neat and easy as it is to follow, is that there are some compounds like ammonia that are bases that don't have hydroxide. So we need another definition. This next definition, called the Bronsted-Lowry model, has essentially the same definition of an acid, a substance that is a hydrogen ion donor. Well, in order to donate hydrogen ions, you have to have hydrogen to begin with. That's the same as the Arrhenius model. And when you put it in water, it donates the hydrogen. There you go. That's the same as the acid definition in the Arrhenius model. The difference in the base model is that it says it's a hydrogen ion acceptor. Now, that means it doesn't have to have hydroxide in it. Anything that accepts hydrogen ions is a Bronsted-Lowry base. Now, how does that work? What does that mean? Well, it's kind of the opposite of what happens in the Arrhenius model. In the Arrhenius model, acids produce extra hydrogen, therefore the balance tips toward hydrogen. So if you start off, level with hydrogen on one side and hydroxide on the other, and then you start adding more hydrogen, it becomes an acid. However, the same basic effect you can have in this if you start out with an equal number of hydrogen and hydroxide, and some compound, this base, if some compound is introduced to the solution which accepts or bonds with the hydrogen ions, what you're doing is you're lowering the number of hydrogen ions, which has the same effect of tipping the balance in favor of hydroxide. You start out with the same number, but then you take away hydrogens, you now have more hydroxides. Without producing any more hydroxides, you've still tipped the balance by subtracting hydrogens. So that's the difference between the Bronsted-Lowry model and the Arrhenius model. The Bronsted-Lowry model is a broader definition. It incorporates more compounds, and it's a little harder to follow because you don't have that hydroxide to look out for in every case, but it's a more complete definition. And here's the other part of the Bronsted-Lowry model, which can be a little bit confusing. So when a base, we said base is something that accepts a proton. Well, as soon as it accepts a proton, it now has a proton that it can turn around and donate. Well, that's an acid. So these are reversible reactions. We talked about reversible reactions in the section on equilibrium. Acid-base reactions are sometimes reversible. And so in a reversible reaction, the base accepts a hydrogen and then can turn around and become an acid by giving that hydrogen back. And likewise, the acid, which has a proton that it donates, well, now it's in a position where it could accept a hydrogen from somewhere else, and that's what a base is. So we have these concepts called conjugate acid and conjugate base. So here's the way it works. The easiest thing to remember is that the acid and the base are always on the left, and the conjugate acid and conjugate base are always on the right. How do you know which is which? Well, HX All right, again, looking at that H at the beginning tells you this is probably the acid. So if that's the acid, what the acid becomes is the conjugate base. So what is the acid HX? What happens to it? It donates its hydrogen and becomes the negative X ion, whether that's a chloride or a sulfate or some other ion, doesn't matter. Once it has donated its hydrogen, it is now a conjugate base. So there's always a pair that goes like that. And they're not always in this order, but you can always link the acid to the conjugate base. Well, in this case, water, when you look at it from left to right, what's happening to it is it's gaining a proton from left to right. That makes water in this equation the base, and the hydronium has that extra hydrogen that it could donate, and that is the conjugate acid. So the base is paired with a conjugate acid that it becomes, and the acid becomes the conjugate base. So the conjugate acid is the hydronium, the conjugate base is the negative ion that was part of the acid to begin with. So hydrogen fluoride, HF, and let's say we put it in, we're going to react it with water. So this is just following the same model we had before, HX, and in this case X is F, fluoride. So the water becomes hydronium. The hydrogen fluoride becomes just fluoride. So the hydrogen fluoride is the acid. The fluoride that it becomes is the conjugate base. The water in this case is the base because it's going to accept the hydrogen from the hydrogen fluoride, which makes the hydronium the conjugate acid. So these two go together, and then these two go together. So acid, conjugate base, base, conjugate acid. Ammonia starts out as NH3, and we'll do it with water again. So what happens to NH3? Well, NH3 becomes NH4 plus ammonium. It gains a proton. It accepts a proton. Where does it accept it from? It accepts it from the water, and that leaves behind a hydroxide. Okay, so the ammonia gains or accepts a proton. That's your base. What it turns into is ammonium, which has an extra proton to donate. That makes it the conjugate acid. And in this case, water is the acid because it's going to donate a proton to the ammonia, and therefore the hydroxide is the conjugate base in this equation. So, as we just saw in the last couple of slides, water sometimes is the acid and sometimes it's the base, depending on what it's reacting with. That property, which water has, is called amphoteric. Amphoteric means it can act as either an acid or a base, depending on the circumstances. So just like ambidextrous means both hands, amphoteric means can be acid or base. Okay, one last thing here on acids and bases, sort of starting vocabulary and concepts. Monoprotic or polyprotic acids. Okay, mono, of course, means one. So a monoprotic acid has one hydrogen that it can donate. So that would be things like HCl, or as we saw, HF, or HBr. Pretty much hydrogen with any of the halogens would be a monoprotic acid. There's no subscript down here, which means it's only got one hydrogen in the formula. Poly means more than one. Okay, more than one hydrogen that can be donated. This means you've got a compound with H followed by a subscript like H2SO4 or H3PO4. Okay, so poly just means anything more than one, could be two or three, and mono means only one. So that's the difference between mono and polyprotic acids. So in the next video, we're going to talk about strong versus weak acids, which is not to be confused with the concentration of the acids, which we will also talk about in the next video with ion concentrations and the pH scale.